Good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. My name is Francesco Petruccione, and I'm the famous director of NITheCS. Or not, I don't know. Anyway, this afternoon, it's a great pleasure to have Professor Markus Böttcher with us from Northwest University, and it's also a great pleasure to welcome Northwest University online. They are in a seminar room like us, somewhere in Potchefstroom. Unfortunately, we don't see them, but welcome if you can see us. Yeah, can we see them, Hank? Northwest University, they should be online. Anyway, okay, welcome for joining us. Yeah, but the start of, here they are. Excellent. Good afternoon. Welcome to the Colloquium Potchefstroom. Thank you. Okay, but the star of the day is Professor Böttcher. Markus studied did his PhD at University of Bonn in Germany, and I think at the Max Planck Institute for Radio Astronomy, which is also in Bonn. After which he spent some time as a postdoc in Texas, also on a NASA Postdoctoral Fellowship. Yeah. From Texas, he moves to Ohio, yeah, first as assistant professor, and then climbing up the ladder to full professor. And in 2013, he accepted a call on a South African research chair for astrophysics and space physics at Northwest University, and he's still there. Yeah? And at the moment, he's also the chair of the South African Gamma Ray Astronomy Program. And I think the talk of today will introduce us to some of the high energy astrophysics mysteries out there. Yeah. So Markus, thank you very much for coming all the way from Potchefstroom, and we are really very much looking forward to your talk. Thank you.
Thank you very much for the introduction and for the invitation to speak here today. Okay. It still says that I'm sharing, but I can just stop it and share again. There we go. Yes. So today I will talk about multi-wavelength polarization in blazars. And as I understand, most of you are not working in astrophysics, especially not high energy astrophysics. I'll start out with an introduction of what blazars actually are. And in particular, they are, So blazars are a very special class of active galactic nuclei. Active galactic nuclei are, as the name suggests, the central regions of big galaxies, the central regions of the size of about our solar system that outshine the entire billions of stars of the rest of the galaxy by factors of thousands or much more than that. At the same time, they're very much variable, so they vary in brightness throughout all wavelength ranges. For me, coming from the X-ray and gamma ray astronomy side, interesting because they are emitting X-rays and gamma rays, so the highest energy form of radiations. In the optical spectra, they show emission lines, which tells us somehow there is gas that is being ionized and excited. When atoms recombine and de-excite, they produce emission lines. The emission is polarized. That's what I will focus on in this talk. And some of them, about 10%, show relativistic outflows, jets that move with almost the speed of light away from that central black hole that powers everything. So what is in fact going on here is that, like probably all galaxies, there's a very massive black hole, millions, sometimes billions of times the mass of the sun in the center of the galaxy. And in these active galaxies, there's a lot of gas around in form of dust, in form of ionized clouds that give us the emission lines that ultimately is fueled down into an accretion disk. So momentum conservation forces the gas to form a disk where it gets closer and closer and closer to the black hole, moving faster and faster, heating up so that it emits ultraviolet and X-ray emission. So this is what an AGN, the central region of the AGN, really consists of: the black hole, accretion disk, a dusty, warm torus of that kind of feeds the accretion, and these broad and narrow emission line regions that give us the optical emission lines. And about 10% of active galaxies, AGN, active galactic nuclei, have these jets, these streams, collimated streams of gas that shoots out from this central region with essentially the speed of light. So now what we actually see depends very much on the angle that these jets have to us. So we're focusing on these radio loud AGN that have these jets shooting out. If we happen to see them from the side, of course, they're randomly oriented. We don't occupy a special position in the universe. So we see these guys throughout the universe from all different angles. If we happen to see them from the side, then we don't actually see much from the central region. So this is radio waves, an image in radio waves with telescopes like, for example, the Meerkat telescope can take. And in these radio waves, we don't really see much of the active galaxy here. This is the galaxy, and we see these endpoints of these jets, these streams, where they ultimately dissipate. They accelerate electrons that radiate synchrotron radiation in magnetic fields. So this is what we see. Mostly we see them in radio waves where these jets dissipate. These jets are actually factors of tens or hundreds or even 1,000 times bigger than the entire galaxy there. So they shoot out over tens or hundreds of thousands of light years away from that central engine. But now, if we happen to see one of these jets almost right face on, then the appearance is quite different. Then I will talk more about these effects. Then there's weird things of special relativity coming into play, that namely the emission from that jet that shoots out towards us with almost the speed of light is much brighter. So we really only see this one jet here. There's the same jet going away to the other side, but that we don't see because that is boosted away from us. And these are the sources that we call blazars, that consist of flat spectrum radio quasars and BIOLAC objects. So where really we see only the emission from one of these jets that shoots out with almost the speed of light, almost in our direction. So blazars are the special class of active galactic nuclei consisting of BIOLAC objects and gamma-ray bright quasars. They are even more extremely variable than all other kinds of active galaxies. They are, in fact, very strong gamma-ray sources. Almost all sources that we observe with gamma-ray telescopes outside of our own Milky Way are these types of blazars. We see, as I'll show in a little bit, in radio images, if you follow them over a long time, that there's knots moving along these jets that appear to move faster than the speed of light, superluminal motion. And as I will focus on in this talk, they are often highly polarized, at least in radio and optical. And the newest development is that we now know that that's also the case in X-rays in some of these sources. So just to illustrate the variability here, you see here time on the x-axis. This goes over a few months or so. And you see the flux brightness over time varying all the way from, this is gamma rays, by the Fermi Gamma Ray Space Telescope, so a satellite-based gamma ray observatory. We see here X-rays, they vary, optical. We see the degree of polarization that I will focus on, how that is variable. So see, everything is variable. And the weirdest thing is that it's not just getting bright and faint kind of in all wavelength bands at the same time. Sometimes that's really correlated, but sometimes it's also completely uncorrelated. They are, in the optical at least, often highly polarized up to about 30 degrees. And everything varies over time. So nothing really stays static. It's the brightness, it's the spectral shape, it's the polarization degree, and also the angle of the polarization. Everything changes over time. If we plot the fluxes, the spectra across the entire electromagnetic spectrum here, so we show here from radio waves to infrared optical, that's X-rays here, and here is gamma rays. We see that these are two non-thermal broad components, very broad components over many orders of magnitudes in frequency, where we have a low frequency component from radio to optical, ultraviolet, and sometimes X-rays. And it's pretty well established that that is synchrotron radiation. For those of you not in physics, synchrotron radiation occurs when an electron spirals in a magnetic field. The electron is very highly relativistic, moves with almost the speed of light. Then it's an accelerated motion that produces synchrotron radiation. And then there's a high energy component from X-rays all the way to gamma rays to the highest energies, where it's not quite established what actually produces this high energy emission. I will mention the two main possibilities. Now we classify these blazars by the shape of this broadband spectral energy distribution, by the position where this synchrotron, this low frequency component peaks. If that is, say, way below the optical frequencies of the visible light has frequencies of a few times 10 to the 14 hertz. If it peaks below that, then we talk about low synchrotron peaked blazars. Many of these are quasars. Some are also galactic objects. And if the synchrotron peak is at these low frequencies, often along with that comes that actually the gamma rays dominates the total energy output. So even though they are already quite bright, say even in the optical, this is the optical frequency range here, they're actually producing much more energy output in gamma rays than in the entire rest of the electromagnetic spectrum. The other extreme, we have sources where the synchrotron peak is actually beyond the optical or UV, also into the X-rays here. Those we call high synchrotron peaked blazars. So classified as such if the synchrotron peak is beyond 10 to the 15 hertz. And in those sources, quite often, the radiative output is dominated by synchrotron. So the gamma rays are there, they're detected in gamma rays, but much fainter than what we see in optical, ultraviolet, and X-rays. And then there's sources in between, so with synchrotron peaks between 10 to the 14, 10 to 15 hertz, that we call intermediate synchrotron peak BLR objects, or intermediate synchrotron peak blazars. So coming back to this point of superluminal motion. So does that mean that Einstein was actually wrong, that things can really move faster than speed of light? Well, that is what's apparently being seen here. So these are high-resolution radio images of one very famous blazar. This source is better known as 3C279 in the community. You can see time ticking away here over years, so from the 1990s up into the 2000s. And one can see this one component here moving out away from this central engine. So the actual black hole that powers everything is in fact a little bit upstream of this here. Now we can measure how fast this is going in angular separation. We know how far this thing is away. If you convert that to distance versus time, you find that in this case, I think it's something like 15 times the speed of light. So how can that be? Was Einstein wrong? I hope not. What's actually happening is this effect. We have this jet component that emits these radio waves moving along the jet, but at a small angle with respect to our line of sight. So we are way off to the right here. What's happening is that the radio waves that this component emits are propagating towards us, but this component is almost moving with the speed of light as well. So it's catching up with the light that it has just emitted. So by the time we receive it, we see it in a much shorter succession than the time that's actually passed over the propagation of this emission region. So we see it happening in much shorter time. I promise there won't be a lot of mass, but you can just say if theta is the angle between the jet and our line of sight, then the actual time that we see passing between the component being here and the component being here is just shortened by a factor like this. I'm just showing this because if you maximize this, you get the maximum apparent speed across the plane of the sky when so beta, is the speed over the speed of light. If we are highly relativistic, then the beta is very close to 1. Obviously, it always has to be less than 1. But if the cosine theta is also close to 1, If it's equal to beta, then you can figure out that this apparent speed is in fact the Lorentz factor with which the component is moving along the jet. So that is this capital gamma, defined as this. For those not familiar with physics of relativity, you can see if the speed is 0, then the Lorentz factor is just 1. If the speed goes close to 1, then we have 1 minus something almost 1. We have the inverse of the square root, so that becomes very, very large. So the more you approach the speed of light, the larger this gamma, this Lorentz factor becomes. And from the apparent motions that we see up to, in extreme cases, 40. So we see blazars where apparently the jet moves across the sky 40 times the speed of light. That means that the Lorentz factors must be of the order of a few tenths to 40. And so that so it moves means that the beta is essentially the speed of light. So that the velocity is essentially the speed of light moving at a very small angle with respect to us. So what does that do? Why does that now make blazars so interesting to study? So a little bit on relativity and special relativity. If, say, this blob that moves along the jet is emitting isotropically, it's emitting the same in all directions in its own reference frame, then special relativity tells us that we, being stationary when it moves towards us, we see this all focused in the forward direction, all bent in the direction of motion of this component. We can define a Doppler factor as this. If we are seeing this close to the line of sight, then that is of the same order of the Lorentz factor. So this Doppler boosting factor in blazars is of the order of 10 or few tenths. The intensity, the flux, is then actually boosted by 3 orders of this Doppler factor. And also the frequency is blue shifted towards higher frequency by this Doppler factor. And also, as essentially the same light travel time effect that gave us the superluminal motion, whatever varies in time in the source, we see varying much shorter by one of these Doppler factors. So that explains why in some of these extreme cases, we see this source that outshines an entire galaxy by factors of thousands can still vary on timescales of, in some extreme cases, just minutes. And if you see something varying on a certain timescale, of course, that gives you an idea of how large it can be. Because, well, nothing can vary faster than the light travel time throughout the source. Because things coming from different regions of the source will take different amount of time to reach us. So the time it takes to travel across the source gives you a minimum of the scale on which something can vary. So if something varies on the scale of minutes, that means in principle it cannot be larger than a few light minutes. And that is a really tiny, tiny source compared to the size of a whole galaxy. But this helps us a little bit to relax that. So the region can actually be larger because we see it moving, we see it varying faster. So in total, if you look at the total output, so an estimate of the total output across the electromagnetic spectrum is given by the peak of plotting frequency times the differential flux. And that is actually boosted up then by 4 of these Doppler factors. And if we then try to infer what's the total energy output is the luminosity, then yeah, we just multiply that by 4 pi times the distance squared. That gives you the total energy output. And if we didn't know about this Doppler boosting by 4 factors of something of the order 10, so this delta to the 4th is then something like 10,000, 100,000, we infer that it's 100,000 times brighter than it actually is, just because of all these relativity effects. That's what makes these blazars so interesting and also makes them easier to study than many other sources, just because we see them so much brighter than they really are. So now, I said, there's a few ideas of what makes this high energy radiation. Remember, we had broadband spectral energy distribution with synchrotron in the low frequency band, and then we had that high energy component. So there's 2 fundamentally different ways how one can make these high energies, the X-rays and gamma rays. And so the simplest models, well, we're physicists, I guess most of us are somewhere in that, at least theorists, so we're well aware of the spherical cow, the joke. So the simplest models then just assume that we have one spherical emission region. And of course, now in the case of a cow, we know that that's a good assumption, that's a good approximation. But for an emission region of a blazar, it's probably a big oversimplification. But surprisingly, even the simplest single zone spherical emission region models do a surprisingly good job in representing many of the properties of blazars. So in these leptonic models, what then dominates is that we have electrons. Electrons being accelerated to extremely high energies, moving with almost the speed of light, highly relativistic. Well, they are subject to other processes, like they cool away, they lose energy by radiation, or they escape. So you get some kind of energy spectrum of the electrons. And then you have synchrotron radiation. That means these electrons spiraling in magnetic fields and giving off radiation that dominates the low energy component here. And if there's only the electrons that have enough energy to radiate, then these same electrons produce the high energy emission by scattering low energy radiation. Compton scattering, there's a lot of radiation that can be scattered, like the synchrotron radiation itself, or external sources, like from the accretion disk or broadline region or dust toruses. So the upshot being, in leptonic models, it's only the electrons that make the entire electromagnetic output from synchrotron and Compton scattering. That means electrons, highly relativistic electrons, scattering up low energy radiation to make X-rays and gamma. An alternative is that we have not only electrons, but also protons being accelerated to extremely high energies. Then we still have the low energy radiation made by electron synchrotron radiation. But now we have these ultra-relativistic protons in there. They can do the same thing as the electrons that radiate proton synchrotron radiation. But they can also interact with low energy photons to make pions. Pions decay, neutral pions to just two gamma rays, or they can produce charged pions. And an important aspect here that would be a whole different talk is that when these pions and muons decay, they produce neutrinos. And a very recent development is that neutrino observatories, especially IceCube at the South Pole, have now measured that there really is an astrophysical flux of very high energy neutrinos that could be produced in these kind of processes in blazars. It's not established that blazars really are sources of these neutrinos, but there's a good possibility, and that would clearly hint at these processes being at play in blazars. Okay, so why do we still study these? Because there's a lot of things that we still don't know, we still don't understand about blazars. In particular, we know there are these jets shooting out with almost the speed of light. What actually powers them is not clear. If this comes somehow, say, from the rotational power of the black hole, or if it's coming from the accreted material. What is the physics of actual launching these? And in particular, what role do magnetic fields play in that? What is the composition? And in particular, what makes the high energy radiation? Is it just electrons? Are the jets just electrons, positrons, or are they electrons, protons? How are particles accelerated? There's a few possible acceleration mechanisms, that some of which, maybe all of them, play a role in astrophysical jets. And also, where is all of that happening? Is it very close to that black hole where you would expect the most energetic things to happen? Or there's evidence in some cases that things are happening still at thousands of light years away. All right, so first thing one might want to try is to see if you have a leptonic model and a hadronic model fits the spectral energy distribution of a blazar. But upshot is, in most cases, you can do just as good a job with leptonic and hadronic models. So either electrons or protons doing the high energy emission, you can do it with both. So we need more than that. We can do that, of course, neutrinos. If we can really associate blazars with neutrino sources, then we know that the hadronic processes must at least be present there. Variability patterns can be different. But what I'll focus on in this talk is that polarization can actually be a very important discriminant of different acceleration mechanisms, different geometries, and also different high energy emission processes. So let me talk a little bit about polarization. So maybe I should have an introductory slide to that. So polarization means we have an electromagnetic wave, light radio waves, infrared, optical, is electromagnetic radiations, electromagnetic oscillations, electromagnetic fields that oscillate as they propagate through space. If the electric fields are oscillating in a preferred direction, that's what we call polarization. If this light would be 100% polarized, then we would have its electric field vectors only oscillating in one very specific direction. That is never the case. It's always a little bit mixed in with unpolarized radiation, but a preferred electric field oscillation, that also means a preferred magnetic field oscillation, means the source is polarized. Now we've talked about synchrotron polarization. I'm sure all the astronomers in the room know about this. Synchrotron radiation means, again, we have a magnetic field, electrons spiraling around. The radiation that comes out is preferentially polarized so that the electric field vectors in the light is perpendicular to the magnetic field. We can associate that to the spectral index of the electron population or the spectral index of the radiation spectrum. And that in this case, if we have a perfectly ordered magnetic field, that means magnetic field in the entire region only one direction, then for typical parameters, something like 70% polarized. So a little bit less known than synchrotron polarization is that also Compton scattering can induce polarization and alter polarization. Again, I believe this is the last formula that I have in this talk. This is the Compton cross-section in the electron rest frame. So Compton scattering really meaning we have an electron, radiation comes in, scatters off the photon into another direction. The radiation coming in the electron, so here we say the electron is at rest. Radiation comes in with an energy epsilon. That's a dimensionless energy where we divide the photon energy by the electron rest mass energy. And then it's scattered off in another direction with some energy epsilon prime. Now, in a regime that we call Thomson scattering, where the electron essentially doesn't lose any energy or doesn't gain any energy in this case, the photon scatters off with almost the same energy. So it's effectively elastic scattering in the electron rest frame. Then the energy before and after is almost the same. So then we have 1 + 1 - 2, and this all cancels out. Then the cross-section is only given by this dot product here. That is the electric field vector of the radiation coming in, and E prime, the electric field vector of the radiation going out. Now that dot product vanishes. If, say, the radiation comes in like this, we scatter it upwards, then the new electric field vector would have to be perpendicular. That doesn't happen because E times E prime is 0. So what's happening is that we prefer scattering where the electric field vectors stay in the same direction. So that means we scatter in a plane perpendicular to the electric field vector. So this is what's preferentially happening, is that we scatter in a plane like this, and we preserve the polarization direction. So that means, for example, if we have a source of radiation coming here from the top, we have polarization vectors. So if the radiation comes in from the top, then we have polarization vectors in all kinds of direction perpendicular to it. But scattering off to the side, we're scattering only those where the electric field vector is perpendicular to the plane of the screen, and that is preserved. So if we look from here, we see the polarization in this direction. And there's nothing perpendicular. So scattering off by something like 90 degrees to the side actually induces polarization perpendicular to the plane of scattering. Now, this is for electrons not moving fast, not being relativistic. If the electrons are relativistic, then all this anisotropy essentially becomes irrelevant, because we have this relativistic aberration effect that the electron sees all the radiation essentially coming in from a small cone from the front, and then it scatters this off essentially back in a similar direction. So if the target photons are unpolarized and we have relativistic electrons making X-rays and gamma rays by scattering those, then we don't expect any polarization in the X-rays and gamma rays. If the target radiation is already polarized, say if that is synchrotron radiation, then some of the polarization will be preserved even by relativistic electrons, but it's cut into about half of the original, say, synchrotron polarization, which again is only a very simplifying case. And in fact, a former PhD student of mine, Chen Zhang, has figured out if we don't have just one homogeneous region where the magnetic field is the same everywhere, if we have, say, some kind of turbulence with magnetic fields going in all kind of random directions, if we have n cells, then in fact it's not just the SSC polarization is not just reduced by the 50%, but in fact the number of cells to a power that's almost 1. So if you have a lot of different cells, you come to a very, very low degree of polarization, which of course is unfortunate if you want to try to measure the X-ray polarization here, because you expect it to be very, very low. Say a little bit about techniques. How can we now measure actually polarization? I'm not going to talk about radio and optical polarization. That would be even, I think it's much better known how we can measure radio and optical polarization. I'm now coming to what's really new. Since 2021, we can actually do this. If we have a detector kind of like this, where you have X-rays coming in through some focusing material, and then the trick for one detection method is that you have a material that just once scatters that X-ray that's coming in, and then it goes out to the actual detector units here. They are essentially in the tube around the scattering material. So then, if we say this is synchrotron radiation coming in, so there's a preferred polarization direction, you would expect the scattering to be perpendicular to the plane of the incoming radiation and the polarization direction. So you would expect the photons that you detect in your detector around it to be preferentially oriented kind of in the direction perpendicular to the polarization direction. So one looks in this detector, in the detector ring around it, for essentially an angular modulation of the X-rays that are actually detected, and that gives you a measure of the X-ray polarization. Alternative is that we measure the X-rays, we detect the X-rays by photoelectric absorption. That means we have some heavy elements here with atomic nuclei and electrons. The X-rays will kick out the electrons, and the electrons are then traced to indirectly measure the X-ray direction and energy. So that's the photoelectric effect. And here, if the X-rays come in with a polarization that's in the plane of the screen here, then the electrons are preferentially kicked out in the direction of these electric field vectors of the X-rays coming in. So here one now looks for an anisotropy where you see this angular modulation with the preferred direction actually in the direction of polarization of the incoming X-rays. So this has now been done successfully. In December 2021 was the launch of the first dedicated X-ray polarimeter for astronomical observations, the Imaging XRay Polarimetry Explorer, that uses this photoelectric effect to measure X-rays and measure X-ray polarization in the medium energy X-ray regime. Let's go a little bit back to these models. What do we expect throughout the electromagnetic spectrum in terms of polarization for different models? So if you look at now, again, look from radio all the way through optical, UV, X-rays, gamma rays, we have some thermal components here. The dust here, the warm dust emits something. The accretion disk will emit something, the ultraviolet primarily. That is unpolarized because it's just thermal radiation. There's nothing that would induce any polarization. Now, this is getting a little busy. So down here, we have the spectral energy distribution. If we have a leptonic emission scenario, then we have synchrotron emission dominating here the non-thermal emission. So that gives you, this would be the polarization, say, of only the synchrotron emission. But where there's a significant contribution from these unpolarized components, then you have more unpolarized radiation than the polarized synchrotron. So that overall, because you can't really distinguish which component you see, it's all just one source. We can't resolve it spatially. It's all just one point that we see. So this all just mixes up. But the polarization goes down where we have a significant contribution of a thermal component. Just like here with the accretion disk, that reduces the polarization that we would otherwise see if it was only synchrotron. Then we have, say, a component synchrotron, Compton scattered, synchrotron self-Compton. That has a much lower degree of polarization. And then there can be additional unpolarized high energy components. So the higher you go, you essentially use lower and lower polarization. So this is kind of a typical thing that you would expect for leptonic high energy emission. If you have hadronic high energy emission, then because the low energy component is exactly the same, but the high energy component is either proton synchrotron, could be this one, or it could be cascading emission. That means pions decay, produce electron-positron pairs that produce more gamma rays and more pairs. That is all synchrotron that's coming out. So the polarization would be much higher in X-rays and even here the soft gamma rays. This COSIZE, the Compton spectrometer and imager, that's a mission concept that is proposed, was planned to be launched in 2027, but now we have to see what happens with NASA's budget cuts. So that is still happening. It's very much out in the open now, but it's something that we still hope to build and launch in 2027 or soon thereafter. So we expect much higher polarization, in fact, detectable levels of polarization in the high energy component as compared to the leptonic models. This, in fact, first studied again by my former PhD student, Harjin Zhang, in his PhD thesis. But here again, we have the spectral energy distribution. So the spectrum essentially from UV to X-rays and gamma rays for in red, leptonic, green, a hadronic model, and showing that in the soft X-rays, we might see a little bit of synchrotron self-Compton polarization here, but in the higher energies and gamma rays, maybe the hadronic model will be polarized, the leptonic model not polarized at all. But this is under the very simplifying assumption that we have one homogeneous magnetic field, as we've seen. If we have multiple zones with turbulence in the magnetic field, then the synchrotron polarization here will be even much lower than this very optimistic prediction. This is very specific for one of these low synchrotron peaked blazars. You can see that the X-rays here are all dominated by already the high energy component, in this case synchrotron self-Compton. And the synchrotron peak is actually way below here, so below the optical. So this is specifically for these low synchrotron peak blazars where there's no synchrotron coming into the X-rays. If we look at sources with somewhat higher synchrotron peak frequencies, there we can have the synchrotron actually kind of peeking into the X-rays. And then you would expect, in fact, measurable X-ray polarization, depending on how high the synchrotron actually extends. Now, there have been people doing detailed simulations of what you might actually see. This was before IXPE observations were really done, saying that, so for these intermediate peaked blazars, if there is a significant synchrotron component in the X-rays, then with some pretty large observing times, you might have a chance to see that. But SSC polarization is essentially not detectable. And that's, in fact, what we see in essentially all of these low synchrotron peak blazars. This is one example. The LSRT is the prototype of the type of blazars that we call the LUC objects. Was observed twice in the beginning, early in the mission. And the upshot was that there was no X-ray polarization measured, only upper limits. And in particular, we see that the optical that is dominated by synchrotron radiation is much more highly polarized than the X-rays. So the X-ray upper limits are much below the polarization that we've actually seen in optical. And that is very strong support for the X-rays actually being dominated by leptonic processes, synchrotron self-compton most likely. The same has been seen for other low synchrotron peak blazars. So that's just a compilation of some quasars and low synchrotron peak BILUC objects. What's plotted here is these polarization parameters, the Stokes parameters, where the degree of polarization is essentially the square of the amplitudes of polarization in two different polarization directions offset by 45 degrees. The 0, 0 means something is totally unpolarized. And you see the 1, 2, and 3 sigma measurement contours all perfectly consistent with no polarization being there. So the picture is very clear here that for these low synchrotron peak blazars, we don't see X-ray polarization. And that very strongly supports that we actually have leptonically dominated high energy emission. One other aspect, one other idea. In very few sources, there's a funny feature known as the big blue bump here. So this is something from the synchrotron component and the high energy component. There's an additional third bump, sometimes soft X-ray access or big blue bump, depending on from what direction you see, from what frequency band you look. And there's a few ideas of what that could be. It could be some part of the underlying accretion disk, maybe with some hot gas around it that upscatters radiation. We call it corona. We expect that to be completely unpolarized. It could be another synchrotron component, maybe another region along the jet with higher energy electrons or higher magnetic fields. That could be moderately polarized. But there's also an idea that you have not only relativistic non-thermal electrons, but also you'd expect in most acceleration scenarios a thermal pool of hot gas and only a tail of non-thermal radiation. We've in fact modeled that with my colleague Matthew Baring from Rice University in a paper 2017, where we used specifically diffusive shock acceleration as the acceleration mechanism, produced self-consistent thermal plus non-thermal distributions, and used that then actually to constrain the relative level of thermal hot electrons and the non-thermal relativistic ones to produce this big blue bump as Compton scattering of some external radiation field on this thermal radiation. And then another PhD student of mine, Lindsay Dreyer, has produced a Monte Carlo code for Compton scattering that traces the polarization of the Compton scattered photons. And she has figured out that in this scenario where you have the just hot electrons scattering external radiation fields, can produce polarization up to almost 50%. So this is two examples. This is the one we just looked at, AO235. There's another example, 3C279. If we have the ideal viewing geometry, then we can get the soft X-rays, in fact, polarized up to almost 50%. So this is something that we still certainly want to test with IXPE at some point to see if we can see this big blue bump strongly polarized or not. But in order for that to be the case, we need the right viewing geometry. You remember, if we have non-relativistic electrons, we induce polarization when we scatter off by 90 degrees. The side, But if we are in this emission blob, we scatter off by 90 degrees, then there's again relativistic aberration. Scattering off by 90 degrees is actually then aberrated, boosted forward to an angle that's about 1 over the bulk Lorentz factor. So here in steradian, the viewing angle, so this is now as a measure as a function of viewing angle with respect to the jet axis. We have to be looking at exactly the right angle of 1 over the bulk Lorentz factor. The bulk Lorentz factor here is 35 in the model simulation. We have to be looking at exactly that angle, and we don't really know what the viewing angle really is. So maybe this is even a way to diagnose our viewing angle with respect to the source, because that is something that's very difficult to constrain independently, because we only see blobs moving across the sky. It's very difficult to say what the actual inclination angle is. But if we look at exactly the right angle, then we can see this almost 50% polarization. If we look at much larger or much smaller angles, then the polarization again vanishes, because we're not in that regime where we're scattering off by 90 degrees, we're scattering off by very different angles. And then that polarization induction gets lost. A little more about low synchrotron peak blazars. If we look through the almost entire electromagnetic spectrum here, from the optical to the X-rays and gamma rays, we focus in here now on the optical regime. This is something where we can do spectropolarimetry. That means we do polarization as a function of wavelength of the optical radiation. That is something that we can do with SALT, the Southern African Large Telescope in Sutherland, not too far from here. The biggest optical telescope in the Southern Hemisphere at this point. Then what we'd expect is, well, frequencies where the dominated by synchrotron radiation should have a high degree of polarization. If there is a signature of, say, an accretion disk coming in towards the blue end, you would expect that to dilute the optical polarization. So in order to see that, you really have to do the polarization measurement in detail as a function of frequency or wavelength. And that was one of the main points of the PhD work of one of my PhD students, H.E.S. who just finished, now postdoc in Michigan, where she has used SALT spectropolarimetry for one relatively high redshift laser. That's the telephone number here at a redshift of 2.1, where we in fact see this effect that towards higher frequencies, the polarization decreases. Also, where there's optical emission lines from the broadline region, those are also unpolarized. You can in fact see these emission lines as drops in the degree of polarization because they also dilute the synchrotron polarization. So we see it here in a flaring state where the synchrotron is very high. We see relatively high polarization. And then about a year later, we observed that same source again when it was in a much more quiescent state. And there it seems the polarization is just very low, essentially consistent with no polarization at all. So here we can then say that most likely it's the accretion disk that dominates everything, because that's not polarized. Something similar we have done together with the H.E.S. collaboration. I did have some slides on H.E.S. and Fermi-Lat, but I thought the talk was probably already getting a bit too long. So if there's questions, so with H.E.S., the largest ground-based gamma ray observatory in the world, we have done a dedicated campaign of monitoring it over many years. And in recent years, also combined that with SALT spectropolarimetry. In 2021-22, we saw one very funny thing here. So in that second panel, you see the light curve in Fermi-Lat gamma rays. You see up until mid-2021, it's very active and variable. And then suddenly that thing shuts off. And it's at very low level. The same in the optical here, that is optical to optical bands, very active and variable and essentially shutting off. And the optical polarization does the same. It's reasonably high polarized before, and then that shuts off. On the other hand, sorry about that. On the other hand, if we look at the very high energy gamma rays, they stay almost at the same level, and the X-rays as well. Nothing much has happened there. So we have X-rays, very high energy gamma rays not doing much, whereas adjacent energy bands doing this crazy thing of being active like crazy and then just essentially shutting off. And that's almost impossible to do with just one single dominant emission region. So our idea was here that we have, in fact, two emission regions, one that's probably reasonably far out, that dominates the very high energy gamma rays here and the X-rays. And then there's an inner one closer in that makes the lower energy GeV gamma rays and the optical. And again here, the prediction is, as we have seen, that when there's a significant contribution from the synchrotron component here in the optical, then there should be this frequency-dependent polarization, exactly as we see. Now it's a function of wavelength here. So shorter wavelength towards higher frequency, the polarization decreases because the accretion disk peaks in there. Whereas in that low state, it seems that whatever the jet was making here is just gone. And the polarization is consistent with whatever interstellar dust might induce. I see I have to speed up a little bit. I'm getting close to out of time. Maybe let's not do that in too much detail here. Let me come to this one. Here's one idea. If we look at high synchrotron peaked BI-Luck objects, then we have the low energy, the synchrotron component, with a peak that is essentially here in X-rays. Now, if we have a scenario like a shock going through the jet, what the shock will do is compress the magnetic field right at the shock. We have a very nice ordered magnetic field. And this is where the highest energy electrons are just being accelerated. And then they lose energy very fast as they drift away from the shock. But the highest energy electrons make the highest energy synchrotron radiation. That would be the X-rays. That should be highly polarized. Whereas if we look at lower energies like optical here, we probe a much larger volume because we probe much lower energy electrons. So we see much more magnetic field structure, much more relaxed magnetic field structure, much more disordered globally, and we expect a much lower degree of polarization. So you would expect systematically in these high synchrotron peak BI-Luck objects that the X-rays are polarized much more highly than the lower frequency radiation. I'm showing this here as something where we see a similar effect, but not just looking at one source, different frequencies, but where we used a sample of optical polarization monitoring of a large sample of blazars of different classes with different synchrotron peak frequencies. And now, as we said, in high synchrotron peak BI-Luck objects, we expect the optical to be probing a large volume disordered magnetic fields with low degrees of polarization. So here we plot as a function of synchrotron peak frequency, the average degree of polarization. Of course, there's a lot of scatter there because the sources are variable, the polarization is variable. But on average, we see systematically for the high synchrotron peak BI-Luck objects, low optical polarization. If we look at low synchrotron peak blazars, then this peak is essentially at the optical or even beyond, or even below, I mean. Then we see the highest energy electrons just making the optical. So for the low synchrotron peak blazars, we see some cases where we have systematically much higher degrees of polarization. So we see this effect also in this large sample from Robopol. And maybe I can go through this a little more quickly. IXPE observations of high synchrotron peak blazars actually systematically show exactly this. They show that there's a significant degree of polarization. Macarian 501 is one of the prototypical high synchrotron peaked BI-Luck objects. It has been observed multiple times. Always we see significant X-ray polarization. And in particular, we see here as a function of frequency for this particular blazar, the degree of polarization. Systematically, the X-ray polarization higher than this is optical, and in many cases, then higher than the radio. You see this here also as a function of time. Systematically, the X-ray polarization higher than the optical. which kind of shows this kind of energy stratification that the highest energy electrons probe smaller regions with more ordered magnetic fields. Now, there are, of course, a few oddballs. This general trend of X-ray polarization higher than optical in high synchrotron peak blazars persists essentially through all HSPs. But then there are weird things like this one here, where we see, now that's the polarization angle. The red and blue points show the polarization angle as a function of time. We see the polarization degree doesn't do much. We see X-ray polarization higher than optical, so the green and purple things are optical and near infrared measurements, lower polarization than X-rays. But the weird thing is, so optical and near infrared, the polarization angle essentially stays where it is. But in X-rays, the polarization angle makes more than a full 360-degree rotation. Now, you can't have that if it's all done in the same emission region or in the same overall jet setup in both the optical and X-rays. So obviously, there's something weird, and I'm not aware of anybody who's been able to properly model this. Kind of the opposite was seen in this high synchrotron peak BLAC object, where again we have X-ray polarization degree higher than optical. Again, it's a function of time here. But here the optical does something weird, kind of does a like 50, 60-degree rotation and then rotates back, whereas there's no indication of any variation like that in the X-rays. So again, that is something that I'm not aware that anybody has properly modeled that, and I honestly have no clue what does that. You see here now combination of, I think that this is still all high synchrotron peak blazars that have been observed so far. We see here the ratio of X-ray to optical systematically larger than 1. So meaning, again, X-rays are more highly polarized than optical. And you can see this here for the different sources that we have X-rays, optical, infrared, radio. So the lower frequency you go, the lower the degree of polarization. So that is pretty strong evidence for this energy stratification in the low synchrotron component, in the low frequency synchrotron component. So a quick summary. So I've said that we can probably probe hadronic particle acceleration through high energy polarization. If we saw any high energy polarization in low synchrotron peak blazars where the X-rays are really dominated by the high energy component, if we saw any high energy polarization, we could make a strong argument for hadronic high energy emission, but we don't see that. So that's actually more evidence for leptonic high energy emission there. I've talked a little bit about this optical spectropolarimetry with SALT that one can use nicely as a tool to distinguish and to disentangle thermal from non-thermal emission components. And for these high synchrotron peaked BLACs, where we see synchrotron from X-rays all the way down to radio, we have strong indications that the X-rays really probe smaller regions with more ordered magnetic fields, and the lower in frequency you go, the larger the region that we probe, the more disordered the magnetic fields are, and the lower the degree of polarization. Okay.
Yeah, thank you very much for these very interesting insights. Are there questions for Professor Böttcher? Please. Microphone is coming from the top. Please.
Hi, Markus. Thanks for a very good talk. My question is there any possibility of Cherenkov radiation in blazars?
I don't think we have a sufficiently dense medium there to actually observe anything that would point towards Cherenkov radiation. Of course, we use Cherenkov radiation on Earth to indirectly detect gamma rays, but I don't think it plays any role in blazar.
There are other questions? Should we ask our Potchefstroom component if they have any mean questions for Professor Böttcher? Any questions from Northwest University?
Yeah, I'm checking here if there's anyone with questions. Anyone?
Yeah, if you turn the camera on, we will see you as well.
Okay. Let's see if there is anyone with questions. Most of them here work with him, so they know what's going on in there. Yes. Come on, guys.
Okay.
I don't see any hands, Francesco.
Thank you very much. Anyway, very nice to see you. Okay, if there are no other urgent questions, thank you very much for joining us this afternoon. Thank you very much, Markus, for the very interesting talk. And according to plan, there should be some snacks and drinks outside. And hopefully there are also some snacks and drinks in Potchefstroom. And there are no snacks and drinks for the other online participants. So thank you very much, everyone. Thank you. Sorry, I've forgotten one important thing. I always forget. We have a little sign of appreciation.